So moving on again. So today it's just going to be about the polynomials, looking at the zeros of the polynomial functions, and then also looking at something called the leading coefficient test. So just to get the terminology out, when we talk about a polynomial function, and we write this form in descending order, f of x equals a sub n to the n plus all the way down to my a naught. We talk about this, we say that this is a polynomial that has degree n. So again, here we just, to have it in descending order, the highest exponent tells me what the degree of the function is. Don't get caught up in the technology, in the wording here. We're just understanding that when we talk about a polynomial of degree 3, that means that the highest exponent is a 3. Talking about a degree 7, n equaling 7, my highest exponent is a 7. So, when we talk about the zeros of a polynomial, for a polynomial of degree n, the function has at most n real zeros. Doesn't mean it has n zeros, or n real zeros. It means at most. It can't have anything greater than that. At the same time, if we look at the graph of this polynomial function of degree n, it has, again, at most, n minus 1 turning points. What is a turning point? Absolutely, as Sean said, it's a relative match, relative min, where it's going from increasing to decreasing. So, that's all that turning point is, and it tells me that most of them, at most, I can't have anything greater than n minus 1. If I have a 4th degree polynomial, I have at most how many turning points?
n minus 1.
3. And n was 4. So I would have at most 3 turning points, 3 relative extrema, 3 times where it's going from increasing to decreasing. When we talk about all this, we're going to use those turning points to help us graph, but we also need to talk about the zeros. So if f is a polynomial, real number, all these say the exact same thing. X equals a is a zero of a function. X equals a is a solution. Of the polynomial f of x equals 0. So in other words, I set my function equal to 0, and that solution is x equals a, which is the same thing as the 0 of a function. X minus a is a factor of the polynomial function f of x. And the point a0 is what is this point? Okay. It's not bless you, but it is correct. An x-intercept of the graph of f. All these are equivalent statements. Knowing that my x-intercept is at a0 is the same thing as saying x equals a is a solution of f of x equals 0, which is the same thing as x equals a is a 0. They all say the exact same thing, whether we're factoring, looking for a 0, or graphing and coming up with that x-intercept. So when we look at something like this, we want to find the zeros of the function and determine the number of turning points of the graph. So, what should we do? Close our eyes and hopefully it goes away.
Yes.
Yeah.
What's that?
Take out the x first.
First things first, since we're looking for the zeros, we also want what?
So it equals.
Absolutely. I want my f of x to equal 0, so And then do what?
So take all the exponent, or raise it on next.
Factor out GCF, in this case from x. And then we have a difficult factoring one here, right? If you have to use the crisscross method, go ahead. But hopefully it is a, when you look at this one, you can see it is just, did I hear a plus? Okay. All right, so x times the quantity x minus 6 times the quantity x minus 6, or just, well, I have three factors that whose product is equal to 0. What do? Set them all equal to 0. So this is going to give me x equals 0 and x equals 6, right? X equals 0, x minus 6 equals 0, or x equals 0, 6. Happened twice here. What's the maximum number of turning points I can have? Two. At most, n minus 1 turning points. N is the degree of my polynomial. What is the degree of this polynomial? 3. So my n is equal to 3, so I can have at most 2 turning points. 2 places where my graph goes from increasing, decreasing, and decreasing, decreasing. We have to find out what n is, and n is the degree of our polynomial, the highest exponent. So always when you get something like this, make sure that you have it in descending order from the highest to the lowest, and say, okay, that very first one tells me I'm dealing with a 4th degree polynomial, 3rd degree polynomial. That's my n. So what degree polynomial do I have here, Dorian? I have a 2nd degree polynomial. My n is equal to 2. So how many turning points can I have at most? Absolutely. Just 1 turning point. Because again, we're using n minus 1. N is 2. 2 minus 1, I have at most 1 turning point. So to find the zeros, we say they're equal to 7, right? Okay. Or better yet, let's say f of x equal to 0. So as a lot of you have already determined, this just factors to x minus 3 times x minus 3 equals 0, or just x equals 3. I mean, look in both of these examples, though, we come up with 2 solutions, but we only write down 1. We have x equals 3 how many times? Over here we have x equals 6, twice. This is something that we call a repeated 0. So when it repeats twice, or even more than twice, and it repeats multiple times, we call this a repeated 0. And this repeated 0, don't get caught up with this terminology here. So as a factor x minus a to the k, where k is greater than 1, yields a repeated 0 of x equals a of multiplicity k. All this says is how many ever zeros I wrote down of that same number. We had x minus 6 how many times? Or x minus 3 how many times? Twice. So it has a 0 of multiplicity 2. If I had, in this case, again, we had our x minus 3 twice. If I had another x minus 3 in there, again, I only have one 0, a 0 of 3, but it would have a multiplicity then of 3. So I'm only going to write it down once because it's just 3, but it does have a certain multiplicity. That multiplicity tells us something about the graph. So again, don't get caught up in this terminology here. That may be a little bit kind of the confusing side. But if k is odd, think about our f of x equals x cubed. It has a multiplicity, my origin, right? That's my x-intercept at 0, 0. Repeats itself 3 times. The graph is going to what? Cross the x-axis. Yes? If k is even, so I have a multiplicity of 2, multiplicity of 4, multiplicity of 6. Something like f of x equals x squared. Here I have a 0 of, what's the 0 of this? F of x equals x squared. 0. Right? Set it equal to 0. I have my x equals 0, multiplicity of 2. Does that cross the x-axis? What does it do? It just touches it. So this is a useful tool for graphing. When we know we have a multiplicity, a 0 of certain multiplicity, we can either determine whether it's crossing the x-axis or whether it's just touching it and going right back up or back down. So we're going to utilize this again tomorrow when we talk about the graphs of these functions. So here we have a nice little function. F of x equals a negative 1/4 x to the 4th plus 3x squared. We want to find all the real zeros, determine the multiplicity of each of the zeros, and the number of turning points. What should we do?
Do you find the turning points before, like, in
Doesn't
the
matter.
original, or like when you computer factor out the x?
So what is n right here? 4. So what is n minus 1? So yeah, it's just whatever n is. So yeah, you don't have to do anything after factoring or something like that. Just take from the original equation. I have a 4th degree polynomial, so I have at most 3 turning points. So how are we going to find those zeros? First thing first is set equal to 0. And we have this lovely polynomial, especially if you love fractions. So if we don't love fractions, what should we do? Multiply by that denominator. Or in this case, if we actually multiply by a negative 4, as long as I do it to both sides, I'm okay. If I multiply it by negative 4, the first term becomes x to the 4th. Second term, it definitely looks a lot better, doesn't it? So now what? Take that GCF, in this case x squared. That's it? Okay, we quit and say, we're done. So what do you go to 0? Absolutely. The 0, x squared equals 0. X squared minus 12 equals 0. So that x squared is what? Just x times x equals 0, or... But how many times do we write it down? So we're going to write it down twice. It's just x equals 0, right? What about the right side? Take the square root of both sides. When we take that square root, don't forget the plus or minus. So we wind up with 3 zeros. 0, positive 2 square root of 3, and a negative 2 square root of 3. What is the multiplicity over here? Well, this is absolutely, this is just x equals, right? My 0, we actually have 2 zeros of 0. It's confusing when I talk about a 0 of 0. But absolutely, so here, This particular 0 has a multiplicity of 2, where these are just multiplicity of 1. So we're going to say multiplicity since it is something that we want greater than 1. Fun stuff. All right, let's look at the graphs of the polynomials here real quick. So, the graphs of polynomials are continuous. What does that mean? Sorry? It doesn't necessarily mean it has to go to infinity. Is this graph continuous? Continuous is if there are no holes, breaks, or gaps. In other words, if I take the pencil off of my paper when I'm drawing it, it's not a continuous function. From start to finish, whether if we're going from negative infinity to infinity, or whether we're going from negative 6 to 5, as long as I keep that pencil on the paper, right, it is a continuous function on that particular domain. Here we have a piecewise function. What is its domain? Yeah, all real numbers, right? It's defined at all points. At this point, it's defined here. But is it a continuous function? No. So, just because you have a function that's defined doesn't necessarily mean it is a polynomial. The graphs of polynomials have smooth, rounded curves. Without any sharp turns. So, the second graph here is a graph of what? Absolute value function. Is that a graph of a polynomial? Go to this first one.
Yes.
Can anyone tell me what the degree of this polynomial is? Caden says 5.
5.
All right. Why 5?
Points.
We have 4 turning points here. 1, 2, 3, 4 turning points. My turning points are defined by n minus 1, therefore n is equal to 5. Correct. This would be a 5th degree polynomial. And that's the stuff that's going to help us again when we graph these. That and also something called, well, we're going to get to that in a sec, our power functions. Power functions are just, when we talk about power function, we're just saying x to the n. F of x equals x to the n. When n is even, it's going to have the characteristic shapes of what? What parent function do you think? It's going to resemble what? Parabola, which is f of x equals. So if I have a graph of f of x equals x to the 4th, x to the 6th, x to the 8th, it's going to pretty much look like x squared, with certain differences as far as a little bit flatter, a little bit steeper. When n is on? A cubic, absolutely. So if I have x to the 7th, I know it's going to look just like my x cubed, or have that same general shape, but stretched out or compressed or something else going on. The larger the value of n, so x to the 7th versus x to the 3rd, what's going to happen when it gets near the origin? Is it going to be flatter or steeper? Well, when you get closer to the origin, what are those numbers? Those numbers are fractions now, right? So 1/2 cubed, is that smaller or bigger than 1/2 to the 7th? Right, so the 1/3 is, the larger the exponent, when I'm dealing with fractions, that number is getting really, really, really small. So what's happening is, the closer I am to the origin, closer I am to the origin, as n is larger and larger, the more flat it's going to be. So if I look at my x squared, f of x equals x squared compared to f of x equals x to the 20th, right? It's going to have that same shape, but right there at the origin, it's going to be a lot flatter than my x squared. So, this is the last thing we're going to be looking at today, the leading coefficient test, helping us determine the end behavior of a graph. What do I mean by end behavior? How it was at the end of the period.
What the graph does after it's done changing.
Absolutely, absolutely. At the end parts, right? When it's done doing its increasing, decreasing, or whatever have you, when it's done all of its relative max, relative min, what's going on with the end? Is it rising or is it falling? What's going on with the end behavior? It's going to definitely help us graph that particular function. Terminology-wise, here's our polynomial. A sub n is called my leading coefficient. So when we talk about a sub n, or the leading coefficient, I just need you to realize that it's just that coefficient of the highest degree variable there, right? Again, you guys don't have to copy all this down. Just understand what a sub n is. A sub n is just my leading coefficient. So our leading coefficient test, it breaks it up into two different things. First of all, if n is even or if n is odd. So when n is, start off with odd. And, well, if n is odd, what are we looking at? What's that parent function that it's going to resemble? A cubic. So depending on whether we're dealing with an even or odd function, right? I'm going to have some sort of characteristics like this. So if a sub n is positive, greater than 0, what's going on? What is it looking like? This one or this one? First one here. So what is happening on the left side? When we talk about the end behavior, we're going to use a little bit different terminology. Instead of increasing and decreasing, which talks about the value of my f of x, we're going to talk about rising or falling. So the behavior, is it rising or is it falling? So right, on the left side we can see that it is falling. And on the right side, so and when we use the nice little math symbols there, so as x approaches infinity, meaning as x goes to the right, my f of x, my function is going to where? To infinity. So as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, so as x goes that way, f of x is approaching negative. Do I have something the same or different with this part? If a sub n, my leading coefficient, is negative? Absolutely. So now it's going to rise to the rise to the left, fall to the right. Yes? Yes.
So, like, you're saying, like, as it's going to the left from the origin, it's going to rise, and as it's going to the right from the origin, it's going to fall.
Again, you're talking about as far as this?
Yeah, yeah.
Correct. When you see that x approaching infinity symbol, that means as I'm going to the right, you can start off from wherever.
Okay.
But if you want to think about starting off at the origin, right. So as I'm moving to the right, what's going on with f of x?
It'll be falling.
Absolutely. So yeah, so here we know on the right side it is falling. So it's going to negative infinity, right? Just like this graph here. And as we go to the right, as we go to the left, it is increasing. We're going to positive infinity. Don't get caught up necessarily with the terminology here. Again, understand this. Hey, if my leading coefficient is positive or negative and odd, I have this particular shape. What happens when it's even? Who knows when that fire drill is? So, if A sub n is positive, we're talking about an even. My n is even. So what's going on? What does it resemble? My parabola, right? So either they're both falling or both rising. So if it's positive, so that means my f of x is always approaching either on the left or the right to infinity. Yes? Oh, wait, this is the last part here, folks. And then in application. And if it's negative, my graph is so again, as x approaches infinity, you have a question? So as x approaches infinity, my f of x goes to, in both cases, okay, just looking like the negative x squared. And just applying this, folks, don't worry. This is the last page, besides the homework. Well, I didn't say it was the next page. So here, I want to talk about the end behavior, the only end behavior. So here we have f of x equals a negative x cubed plus 4x. What's going on with the left and the right?
So just like identifying which way it goes.
Absolutely. We're just saying what's happening on the left side, what's happening on the right side. Is it rising or is it falling?
It's left and right to the right. That falls to the right and right to the left.
That's the one he says. It's going to rise on the left. Because, why? We're talking about a negative. All right? X cubed has it falling on the left, rising on the right. Negative x cubed, opposite, right? Such as, so here, especially when you're graphing, you may want to put some little indications here. This is what's going on, so we need to sketch that graph. What about this? F of x equals x to the fourth minus 5x squared. And x to the fifth minus x. So it's going to resemble that same end behavior of my x cubed. So falling on the left and rising on the right. Question? It was. This was a lot of writing, and again, tomorrow I highly recommend you print out those notes, folks. When we do these graphs, it's going to make a lot less writing, same thing said, when we do those particular graphs. So, next page. This is page 1, though, folks. So let me know when you might want to go to page 2. I'm serious. This is page 1 homework. So get it down. We're not graphing anything today. Tomorrow we will. And there may have been a lot of writing on this particular one, busy defining a bunch of stuff, but concept-wise, we really didn't go into too much things here. You guys ready for the next page? Yes, no? This one you guys can finish in 2 minutes. Actually, 1 minute probably. Just like we did in that last example, all it is determining the end behavior of a graph. Oh, I'm sorry. 55. I was wondering what the...